So it's a pleasure to introduce the next speaker, Davide Gori from the University of Roma, La Sapienza. And he's going to talk about alternative modular compactification of MGN via cluster algebras with applications to the MMP of MGN bar, right? It's the talk. It's the entire talk.
Thank you for the invitation here. So in this fast talk, I would like to present a precise result, or let's say a result from my thesis. So let me first state the result, and then we will see the ingredients, and we'll try to get into some details. So first of all, as a disclaimer, I work over a perfect field of characteristic big enough, but let me be vague about what does it mean. So the theorem is the following. So take an integer g greater than 2 and define the following space as the quotient of the rational Picard of mg 7 over 10. So this is a stack of curves of genus G I will define later over the Picard of the moduli space that I will write as a mathbb of 7 over 10. So there is this 7 over 10 and also this number. I will say later why. It's just a number now. We'll see later some details. So the theorem is split in two parts. First part is the following. So there exists a complete fan sigma in EG, and this is actually a rational and polyhedral fan. Yeah.
Sorry, what's the difference between the two ends?
Yeah, this is the moduli space, and this is the classifying stack of curves that I will define later. Good. So there exists a complete fan in AG such that we can establish a bijection between the semi-stable loci with respect to an element in AG and I will explain later what does it mean semi-stable loci and the cones of C. And the bijection is given by sending mg 7 over 10 semi-stable to the cone that contains in the relative interior the element L. Oops. Good. And the point of the first part is that we have a complete description of sigma as the cluster fan of type A1 times AG minus 3 over 2 if G is odd, and A1 times C of G minus 2 over 2 if G is even. So let me just say, I won't go deeply in explaining what is a cluster fan. And the idea here is there is a combinatorial structure that completely describes sigma. And moreover, to completely describe this, I also need some extra data that I'm not writing here. But let me just say that this has a somehow clear combinatorics. Good. So this is somehow the description of the semi-stable loci. But there is a second part of the theorem that is in birational geometry, that sigma is the Q factorialization fan of mg, the moduli space, 7 over 10, and the partial Q factorializations are given by the moduli spaces of the semi-stable loci above. Okay. Now that we have the theorem, let's see. First part of the remaining talk, I will explain what is this object. Then I will say something about the L stability here. And then I will go through the second part, is somehow a birational picture of what's going on here. And I will explain what is the cofactorialization fun. If there's time, I will say something about the cluster fun. Good. So let me just say that there exists an analogous statement for market points, but it's way more, a bit more involved, and it's useless now to state it in big generality. Good. So part one. Let me define the mg7/10. So this is the classify curves C of genus G such that 1. They have mild singularity. So C has singularities of types let's say, nodal singularity, cuspidal singularity, and tacnodal singularities. So nodal singularities are the ones that appear also in the Riemann-Form compactification. Cusps are locally y squared equal x to the cube, and you can picture that way. Tacnodal is somehow a generalization of this, and locally is y squared x to the 4, and are given is a B-branch singularity where the two branches attached tangentially. And we also require here some standard, let's say, requirement, that is, we ask that the log dualizing sheaf, that in this case is a line bundle, to be ample. Second condition, we disallow elliptic tails. What does it mean? It means that every curve here does not contain a subcurve of genus 1 that you can picture that way, let's say of genus 1, attached to the rest of the curve, that if it is attached nodally, is of genus G minus 1, but we also remove the case when this is attached via tacnodes, and in this case, the remaining part is genus G minus 2. Good. So at least now we have a definition, and now let me explain why 7/10. So theorem by Hassett and Eon in 2008, they proved that this stack has a good moduli space, so has a moduli space that is called mg7/10, and moreover, this guy here is isomorphic to a log canonical model. So it's the proj of some ring of section of a line bundle. And this line bundle lives on the Riemann-Form compactification of the curves, and is given by the canonical plus 7/10 delta. And delta is the total boundary of this stack. So this is the reason why we see 7/10. Good. So it's quite beautiful that we have an isomorphism between this canonical model that a priori doesn't come as a good moduli space of some moduli, so of some stack of curve. And so, moreover, this is an alternative compactification of the moduli space of smooth curves. So somehow this links this space to the birational geometry of MG. And let's say, more in general, there is this Hassett-Kiel program that has an attempt to understand the canonical model of MG that is highly involved in somehow is related to the birational geometry of the Riemann-Form compactification of the moduli space of curves. So the Hassett-Kiel program tried to understand this, simply trying to understand what are called the log canonical models. So we take k plus alpha delta, where alpha is a rational, and we try to do the same model, and we imagine to slide alpha to 0. When we hit 0, we have the canonical model. And when we think to slide alpha to 0, we see some wall crossing. And if alpha is big enough, this wall crossing is known. And in particular, the beautiful thing is that this wall crossing correspond to the first, to first possible steps of the minimal model program of the Riemann-Manifold compactification. And moreover, they arise as moduli spaces of some stack of curve that gives alternative compactifications of MG. So in this sense, there is this modularity conjecture that basically every space that we see for alpha decreasing to 0 arise as a moduli space of curves. So why 7 over 10 is important? It's important because somehow it's the first value where this picture is not trivial, in the sense that it's the first wall where you see something that is a flip in the minimal model program. Good. So let me, now that we know what is MG7 over 10, let me explain what does it mean L stability. So for a second, assume that X is a quotient stack where Y is projective, G is linearly reductive, and we fix a line bundle ample with a G linearization. Good. So classical GIT tell us that we can construct, at least we can define a semi-stable locus inside Y. There is an open such that if we take the quotient, this semi-stable locus is G invariant, and if we take the quotient, this is what is called a good quotient. And so this semi-stable, this Y semi-stable strongly depend on the choice of L. And if we have this kind of stack, what turns out that we can define more general for stacks that doesn't have you cannot write that way. You can define a semi-stability with respect to a line bundle. And in this particular case, the semi-stable locus is exactly the quotient stack given by the semi-stable. And this guy has a good moduli space that is exactly the space, the good quotient above. Good. More in general, proposition. If we start with a stack with a good moduli space, we have that we can define a semi-stable locus that is, again, an open in X that has, and this admit a good moduli space. We ask X to be finite type over K, let's say safe. Good. So in our case, we recover, we take X, MG7 over 10, and we recover exactly this semi-stable loci. And let me say just some things in words. First of all, in our specific case, the moduli space gives us many alternative compactifications of MG. Moreover, these alternative compactifications are somehow automatically projective. And let's say, leveraging on this technique, we can understand all the possible compactifications of moduli space that arise of MG that arise modularly with as stack of curves, as good moduli space of stack of curves with singularity of type node, cusps, and tag nodes. Good. As a last remark, some of these compactifications, like the semi-stable loci MG7 over 10 semi-stable, are already established in the literature, and for instance, we see the Schubert compactification, and others were established in an article, more recent article by Codogni, Tasin, and Viviani. Good. Now that we have this picture, let me say that somehow we completed, at least we can have an idea of what does it mean, the first part of the theorem. And now let's move to the birational picture. So, okay, sorry. First, before moving to the birational picture, let me just say that the semi-stable locus usually can be computed with what is called the Hilbert-Mumford criterion, that basically take a point, and in order to understand if this is stable, take any possible one-parameter subgroup, consider somehow the flow of this point around this one-parameter subgroup, and what happens is that you have to compute some weight, and if the weight is I don't know, negative for any one parameter subgroup, then it's stable. So there is a more intrinsic notion of the stability that is called theta stability that can be defined without having a quotient stack, but more in general. And this is what we use in our case, and this is our definition of L stability or L semi-stability. Good. So last picture. So let's start with X, assumed to be a normal projective variety. So X is said cofactorial when every Weil divisor is up to a multiple a Cartier divisor. So in general, we have that the rational Picard of X is included in the class group, and it's a cofactorial when this is an equality. So let me define what does it mean to be a partial cofactorialization. A partial cofactorialization for a variety that is not cofactorial is basically, the point is trying to find another variety that is birational to X that now is cofactorial. So in general, we call a partial cofactorialization let's say, a variety plasmorphism that we ask to be a small projective contraction. And in this picture, we have that via pullback, we can include the Picard of X inside the Picard of Xi, the rational Picard, sorry. And this lives inside the class group of Xi that, given that it's a small contraction, that means that doesn't contract any Weil divisor, this is exactly the class group of X. So somehow a partial cofactorization is something that increase the Picard rank. So this kind of singularity is very important for the minimum model program, because in order somehow to perform flips, we need cofactorial varieties. And in this, under some beautiful assumption, we have that the class group of X, let's say if X is KLT type and is not cofactorial, the class group of X modulo the Picard has a Wallen crossing decomposition given by, you take all the possible partial cofactorialization, you take the relative Neff cone, that are the line bundle that vanish on the curves that are contracted by this partial cofactorialization. And this gives you a beautiful Wallen crossing picture. And the point here is that if we consider mg 7 over 10, we have that sigma is our Wallen crossing picture. And moreover, let me say, in this case, we can also understand what is the relative Neff, what are the relative Neff line bundle and what is the Picard, and we can understand the Picard in exactly the Picard and the relative Neff cone for these maps. Sorry, I forgot to mention that all this thing is done because mg 7 over 10 is not cofactorial. So somehow indeed, this reflects on the fact that it's the first value where you see a flip in the asset kill program. And given it's not cofactorial, you can run this thing where X is mg 7 over 10. Good. So in the last 1 minute, probably, I don't know. Yeah. OK, so now at least we have all the ingredients here except this thing of cluster fun. So let me just do an example. If we take g equals 7, for instance, if we look to the equation, we have something that is type A2 times A1 that, even if you don't know what does it mean, it doesn't matter. This is the fun. So there are 5 maximal chambers times A1 that is the unique fun of dimension 1. This is of dimension 2. Good. And here, what happens is that, for instance, if we take the positive chamber here, we see the Schubert compactification. And moreover, here we can see all the Picard group of the stack. And we have a beautiful picture with the flips, because in general, we can understand the wall crossing in these pictures as flip in birational geometry. So if we imagine to have 2 cones, and we have 3 line bundles, L1, L2, and L, that gives you L stays on the wall, then we can consider this. So now let me drop the 7/10, given that it's clear what are the spaces I'm picturing here. And this picture, we have natural morphism between the spaces of the cone to the space of the common face. And what happens is that this is a flip. And in particular, if alpha is this ray here, and alpha is an element, again, in EG, then this is exactly a minus alpha flip when we think this alpha as a line bundle. I think I'm over. So let me stop here.
Thank you.